Yes.
Yes, sir.
Okay. So let us start. So, like in previous session, we talked about like what are the important components to be considered whenever we are really talking about designing an assembler. So on that particular point, we even discussed about what would be the important aspect that need to be addressed by us in respect of talking about those different data structures which are major components of the system. So we said we will require definitely something called as search algorithms need to be designed or defined by us depending upon how the data structure is built and so on. So we'll move further and we'll now try to introduce one component in the diagram that we saw. The reason behind, like if you recall what we saw different types of assemblers in one of the class. So at that time we said that every assembler will have to go through the source code given as an input so as to translate it in terms of an object code. Now, while completing that process, it may need to see the source code or visit the source code maybe a number of times, depending upon what's the procedure, what's the methodology applied to implement such a assembler. Now, when we do deal with this, like what are the number of visits that we are going to apply? So let us define a term called pass. Now, this pass term would be helping us to really understand how many times you are visiting the source code. So like we'll be talking about right now, mainly a two pass assembly scheme. And towards like when we finish this two pass assembly scheme, we'll be talking about one pass assembly scheme. Now, when I say two pass assembly scheme, ultimately uh, it means what? How many times we are going to visit? Two times. Correct. So like as I said, we are considering two approaches for designing an assembler. So first methodology is one pass assembler and second methodology is two pass assembler. But we are starting with two pass assembly scheme because I want you to implement a sample assembler, a toy assembler, which would be taking into consideration this Intel 32-bit instructions. Okay, what are the problem statements that I talked earlier about? Like for example, it should be permitting you adding two numbers, multiplying two numbers, computing factorial, and so on. So when we say this, how exactly we are going to build these data structures? Right now, even we are not sure about how our final file should be visible. Correct? How our final file should be visible. So we are going to mainly think of some major components with respect to our system. So let me share my screen. Okay, so we are going to make mainly use instruction pointer. Now, as I stated earlier, like when I gave you a task to be done, assignment number 3, where you were expected to translate the data given in the form of data in data section or RO data, even the BSF section. Correct. So these three things we have identified in LST file that each of them is starting at 0. So when it is starting at 0, how exactly it differentiates between the elements that are occurring or appearing as a part of it. So that's the thing. Like what we are doing, we are assuming that though we are not going to call it as instruction pointer, but there would be some mechanism which would be used. So this instruction pointer we are going to make use of for the text section. Correct. But other variables which we are going to make use of like for this data, BSS and arrow data, we'll use some name, like maybe some counter. So data or location counter would be best thing for us to represent it. The position of the particular entry in the respective data structure. Correct. So when we really work, when we really think of implementing the data structures that would be appropriately used by us for different aspects. OK, so we will require the data structures to be defined appropriately, considering their own design. Now this, when we said that we are talking about a two-pass assembler, we will have to understand that this assembler would be performing two visits over the source file or source code. Now let us differentiate what exactly they are going to do in the two-pass scheme. So two-pass assembler. So in this two-pass assembler, it is going to consider first pass, where it is supposed to read the entire source code given as input. Correct? Given as input. This would be the task. Now, what exactly we are going to do while going through this source code? We are going to do a specific task. Source code given as input, where we are supposed to look for label definitions. Correct. Now, when I say labels, they would be what? Like, for example, main, printf, scanf, or LP, the kind of label that we used earlier. Correct. So they may be either of the form. Moreover, it would be taking into consideration the identifiers declared in these data sections. So collect identifiers from data, BSS, and RO data, depending upon whether they are part of your code or not, part of your input code or not. Correct. Now this would be our task in the first pass. Now, while we collect all these labels, after collecting all labels, we will assign values and are to be added in symbol table data structure. Symbol table data structures. Now we specifically know how these labels would be occurring. They have a standard form. They have the standard form. How they would occur, like before DB, before DD, before RESB, before RESD, correct? Even before colon, with global, with extern. We know these forms that symbols would be occurring with this case. Now, in this whole process of the first pass, we are not going to translate any of the instruction. Translate, I mean to say, in general, we say assembly. We assemble any of the instruction. We are not supposed to, because we specifically know now that how the labels would be occurring, how the symbols or identifiers would be occurring. Are you with me? Yes.
Yes, sir.
Yes, sir.
Okay. Now, when this is done, after end, what would be output of this process? What would be output of this first pass? Output of this pass is what? Symbol table is populated. Symbol table now contains all labels, identifiers defined in the source code. Correct? Defined in the source code. Now what would be now second pass? Now second pass. Now with this second pass, we have to read now the instructions. Now those instructions are to be assembled by making or taking help of, by making use of, or by taking help of the symbol table that you have built in the first pass. Correct? So input would be what? Will be source code again and symbol table. Source code is given, symbol table is outcome of your first pass. Now here I am not mentioning anything about literal right now. This in general I am talking about. Now minute details in respect of implementations can be added at the separate point of time. At separate point of time. So we don't care about now other parts other than symbol table and source code. Input will be source code, symbol table. And what do you think? Other inputs to be? Other inputs would be opcode table. Information about directives, declaratives. Okay, now declaratives in some sense probably are taken care of in the first phase only or first pass only. So I will not now mention about the declaratives, but I definitely would be writing about information about directives, registers, etc. Because we will require when we have to translate an instruction to get mod RM byte, to get SIB, will require definitely these registers. Now whether we'll be able to implement SIB or not, that's another question. But right now, let us assume we may probably go along with it. Now next thing would be what? Like when this would be input, output would be what? Object code. Okay. Now you can have one option here if you want the way that we do apply. Say for example, let me go here. ls. Okay, let me remove rm star.o. Now let me take this pgm2. This is my code. Correct? This is my code. Now what I do is I write NAS. Now you will see that pgm2 star. I can see that only these three files are. Let me remove that lst2. I have only these files, these two files. One is backup, other one is the current file now. Now let me open using NASM. So NASM -f elf 32 pgm2.asm. Now when I apply this, and if I consider now this command, If I fire this, which file gets generated here? An object code. Correct. So if I remove this object code now, and if I fire a command like -l pgm2.lst. Now if I see this, what happened? My pgm2 also got generated. So when I generate this -l, if I wish to provide output, I also can permit user to generate listing. Correct? Listing using list mode. If user specifies -l, correct. When we gave dot dash where is NASM? Yeah, when we give this command, it generated this only, not an LST file. But when we gave this, because we deleted that .o2 earlier, when we gave this, ultimately it generated .o as well as .lst, because earlier was 30, we deleted it. Now it is 31. So both of them got generated at same time. So I can provide these options, command line arguments for my code while taking the input file. So say for example, it would be like this. So my ASM would be your assembler. Then you are giving, okay, generate an object LST file. So you will give -l pgm2.asm. So it should generate LST file and object code. And if I don't give up this, it should generate only .o. That's how I want you to implement it in some sense. So here in this case, my ASM is your executable code for your assembler. My ASM is your executable code. PGM2 would be some kind of assembly code which is given as an input by you. Correct? Some kind of assembly code that is given as input by you. Now next is what? When we have this thing with us, this is the rough idea now I got, or we have decided that we are going to work with. But then what would be importance of first pass? What exactly we are going to do? We are not going to use only symbol table. As we already visited the file, we should create some output as well, apart from the symbol table. And our output of this pass expects something called as intermediate file. And what this intermediate file will have? Collection of records line by line. So let us think of how that record will look like. So first of all, let us say it is record type. Record type would be what? Whether it is instruction, directive, comment, or an invalid line. Invalid line means what? It is not expected to be there. Say for example, how that invalid line would be. Let us think of. Section dot text global main colon move px comma pbx. NASM -f ELF 32. Now you can see label alone on a line without a colon might be an error. There's a warning given. So this may be an invalid line. Line number 3. Line number 4, label or instruction expected because colon was added. If I see that code, see the code. Line number 1, 2, 3. 3 it says label alone on a line for this main. Without a colon might be an error. Correct. 4th, this is an error. Label or instruction expected at start of line because you wrote only colon. Now if I do this, if I make this change rather, and if I put here semicolon, and if I translate this now, there is no error. If I show my code, now this is a record type. It says it identifies it as a comment value. Now when I translate this code, you will see that that comment also is treated as a line. Can you see that? Now, when we said that the source code needs to be revisited twice, but then why should we do that? Because if at all, again, I'm going to revisit everywhere, where is my symbol table entry? Where is the instruction, whether it is the instruction or what? How do I differentiate? When we say that, though we wrote here some output of first pass to be symbol table now contains all labels or identifiers defined in source code, but it has to do more than this. Though it is not going to translate or assemble any instruction, we need to keep information about whether it is an instruction or it is something else. That means what? We have to determine what is the size of instruction. The reason behind is this. You have to calculate the addresses. Say, for example, again, let me go back to this code. Now let me translate this. Now let us see that LST. Now you see here, you can see here that we have to compute size. How much size this took? Because it takes 4 bytes. 1, 2, 3, 4. That's why next address goes to 4. 0, 1, 2, 3, 4, 5, 6, 7, and so on. Then if another variable is, then you could have seen that it would be starting at 16, 17, 18. So 19. So if I add one more variable there, it will start at 19. You can see here, it starts at 19. So we need to count this size as well. It's not only about instruction, but data part also. Because I want to generate this LST. Same thing possibly could be true for this. So I have here one variable C. It starts at 0. Correct. Let me add one more. Now see, it took 4, 4, 4, 4. Correct? 4. The next address would be at 4. 4 plus 4, 8. So next address would be at 8. Now if I add one more, so ultimately it would be like for us like 38. But what it would be, let us check. So if I convert that 38, that ultimately 38, like if to hex, probably I may get 26. I don't know, but this is an address shown there because it has to add 0, then 4, then 8. From 8, compute 30 bytes addresses 8, 9, 10. 10 means A, B, C, D, E, F. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 1A, 1B, 1C, 1D. Go on. Correct. So at some point of time, you will reach to 26. Because 1F would be there, then 20, 21, 22, 23, 24, 25, 26. Next address would be at 26. Same thing, we have to compute size, how much this instruction may take. That means we have to identify what is size of this instruction. That means what? It has to consider the opcode table also. So instead of taking that opcode table here, I will try to use this because I will require that somewhere here as well to compute that size. And we know that, like, what is the difference between two instructions? Like this is taking input as register. So register addressing mode. So we are deciding if addressing mode is register to register, then size should be what? So if you see, all these three instructions are different: move, add, XOR, but all of them are taking only 2 bytes. If I change them to 16-bit operands or registers, I do see that they would be of 3 bytes because 66 as a prefix would be added there. That means what? We may have to search for the mnemonic table as well or opcode table as well. Because we have to decide, depending upon what the operands are, what is the addressing mode, and that addressing mode would be defining size of my instruction. So maybe in my opcode table, I will use a column called size, probably, which will help me out because otherwise I have to compute it always. So what would be the possible instructions for me whenever I'm talking about? So let me add here move ex comma 10. Let me add it here as move add ex comma 10. Let me add here XOR ex comma 10. Let me see now what is the difference when I add immediate data there. Now do we see some change? With move, size is different. But when we do talk about add and when we talk about XOR, so most of the arithmetic instructions probably may take 3 bytes to 5 bytes. Right now 3, considering mod RM. Maybe it may go to 6, not 5. 3 to 6 because mod RM would be involved. So 83 probably is an opcode for XOR. F0 is probably the what you can call it as mod rm for it. But you may see like when I wrote add, when I wrote XOR, both of them are representing 83, 83. Then how do I differentiate whether it is add or XOR? Similarly, if I add again, I am getting 83. So whenever it is with immediate data, this mod rm would be defining what kind of instruction it is, whether it is subtract, XOR or add. This mod rm would be defining. Is it really a mod rm or it is talking about 2-byte instruction? So let me take help of my manual. Let us go to add. Let us talk about immediate. So it is 83. Correct? So it says /0. So if similarly, if I go to sub, it is saying /5 immediate. Similarly, if I go to add XOR, sorry. XYZ. Let us talk about XOR. 83. It is 6. Correct. So it is telling me this slash number for mod rm is telling me that yes, what exactly it is. That 6 would be telling which kind of instruction that it is XOR. 5 would be telling me it is sub. 0 would be telling me it is add. So there might be few more instructions similar to this. Let us write or and let us see whether what they do. Or and okay. Let us check. We also got again 83. So if I see now the manual, so we added what? And let us check and it is /4. So it is in the order probably. It is having following something, some mechanism which is differentiating what kind of data, sorry, what kind of instruction you are using with opcode to be 83. So this is a strategy applied by your assembler. So you may take a call to make use of same thing, or you may think of some other mechanism. But now we will require that information because we have to compute size of the instruction. So while considering or while building this opcode table, you may have to consider these all aspects. So what would be then record type? record type would be this. Then we will require something as instruction pointer, or I will use location counter. Now let me use this location counter or address probably to keep information about the addresses which are generated every time when I do see that LST file. See here. I have to keep track of this. I have to keep track of this too. I have to keep track of this too. Correct. So I would be using some mechanism for the line. This would be for each line. Now I need to find out entry because my opcode table would be there. Now suppose if I get this instruction or I am not picking opcode of that because I'm not translating it to this. Let me add a pointer here. So my some sample instruction would be like this. Suppose if it is OR. So let us say OR is my 89th entry. 89 hash. In opcode table 89th entry. Opcode table may be different. Example, sample case. If I organize this in a serial manner, my opcode table, some order, following some order with an alphabetical or maybe grouping them in terms of their operation strategy and so on. So 89th entry is say for example OR. Then I am talking about registers. So EX, first operand, reg 1, second operand, reg 4. So this kind of format would be. Along with this, like when I got this, I'm adding size here. 3. So when I say see next instruction, probably it is 78. 78 entry. So now it is reg. Say for example 1. Then I have immediate data. So this immediate data, how do I translate this? Now it would be dependent on what kind of instruction it is. Because one may see here, whenever it is arithmetic instruction, apart from move, like or, though we say logical instruction, arithmetical or logical instructions would be taking exactly 1 byte, 2 byte or 4 bytes. But move always will take 4 bytes to write this number into hex. So you may have to identify now in how many bits, what would be the conversion. So I'm saying it would be literal table entry. Example, I'm assuming literal 1. Now size is again 3. Now when I write size 3, ultimately it means I have to only take here 1. 1 byte, that means 0A is to be written. Now if it is move, say 114, entry number 114 in opcode table, register 1. Literal number 1, but now size would be 5.
Hello, sir.
Yes.
We have a data structure quiz at 10.
Okay. In one, we have 5 more minutes. Okay. Is that fine? So within 2 minutes, I will finish. So now in this case, this will let me know that how my literal should be written. Like the way that I saw here, my literal is written like this. My literal is written like this. My literal is written like this. The constant value. This is how I'm going to proceed further. Okay, so I will stop here. I will let me add this file probably.